We just did a little experiment where we tested dropping two different objects toward the ground, and we wanted to see which one hit the ground first. We dropped a set of keys, and then we dropped a piece of paper. The paper was crumpled up, and we found when we dropped the two of them that they both fell at the same rate. They both hit the ground at the same time. They both fell at the same rate. In the absence of air resistance, that will happen every single time. In the absence of air resistance, the rock will fall at the same rate as the feather. Now, we don't really ever have no air resistance, but we're going to approximate our situation over the next couple of days as if we don't have air resistance. The rate at which everything will fall in that case where we don't have air resistance is, well, we've said over the last couple of weeks, we've alluded to this a few times, they fall at about 10 meters per second squared. Well, the exact rate is actually 9.81 meters per second squared. That does vary a little bit depending upon where you are on the Earth as well. Maybe it's 9.83 somewhere, maybe it's 9.78 somewhere. The closer you are to the center of the Earth, the more gravity is. The further away you are from the center of the Earth, the lower gravity is. So in other words, gravity would be slightly lower in Calgary than it would be in Vancouver, but not much. Maybe a difference of about 0.01 or 0.02. Yep. Now, just like things fall at a rate of negative 9.81 meters per second squared, things rise at a rate of, and slow down at a rate of negative 9.81 meters per second squared as well. Throw those keys up in the air. Gravity is gravity, right? It's the Earth that's affecting these keys. Watch when I throw them up in the air. They slow down. They stop when they reach a max height, and then they fall back down. The Earth isn't any different on the trip up for these keys than it is on the trip down for these keys. So if the Earth is what's causing the gravity, then the acceleration of the keys must be the same on the way up as on the way down. The difference is this. On the way down, they speed up in the downward direction. When they speed up in the downward direction, we make it negative 9.81 meters per second squared. We speed up in the negative direction. But as the keys are rising up into the air, they're slowing down in the positive direction. Well, slowing down in the positive direction also gives us a negative 9.81 meters per second squared. So speed up in the negative direction, slow down in the positive direction. Any way you look at it, the acceleration will be negative, and specifically negative 9.81. So in general, as I just said here, acceleration is negative when it slows down in the positive direction, going up and slows down, or speeds up in the negative direction. That's convenient. I mean, we can't just say that for convenience sake. It has to be physically and mathematically correct, and it is. But it is still convenient, because in the end now, we can analyze the keys flying through the air like this, and we don't have to make it separate problems for the trip up and the trip down. Right? The acceleration is the same. So whether we look at the keys going up or the keys going down or a combination of going up then going down, it's the same problem. We don't have to break it up like we did that quiz question on Friday where something happened and then something else happened. The same thing continues to happen even as the keys reverse direction and come down. We just finished looking at velocity time graphs. In fact, we checked over a little bit of homework on Friday on velocity time graphs. Let's plot a velocity time graph. Let's plot a velocity time graph here of an object being thrown up into the air. Okay, got it? A velocity time graph of throwing those keys up into the air. They stop when they reach the top, they reverse, and they come back down to the bottom. I'm going to give you about 30 seconds right now to see if you can sketch that graph. No numbers, just the shape of the graph, and then we'll take a look at whether you got it correct or close in just a few minutes once you're finished. Here's what it looks like.
Yes, I got it right.
Why does it look like this? Well, because in the end, when the object is going up into the air, the keys are going up into the air, they're slowing down. Now, the rate of acceleration is constant. The rate of velocity isn't constant, but the rate of acceleration is. They're slowing down. It's a constant acceleration. It's a straight line. But it's a decreasing velocity, right? It's a decreasing velocity. Until they reach the peak height, they stop. And then what happens? Well, they speed up. The velocity gets bigger and bigger and bigger and bigger, but in the downward direction, in the negative direction. So this is what it's going to look like. All right? We got a problem here already. The good news is this problem is very, very much like some of the problems that we've done before. It's an acceleration problem, right? Except this time we have one more given. We have the value of the acceleration. In fact, in all of the questions involving gravity, we have the value of the acceleration. It's going to be negative 9.81, whether it's going up or whether it's going down. So here's the question. Page 57. While cliff diving in Mexico, a diver throws a smooth, round rock straight down with an initial speed of 4 meters per second. The rock takes 2.5 seconds to land in the water. How high is the cliff? A few summers ago, my brother-in-law and sister-in-law have a place out in BC called on a lake called Maple Lake. You guys know where that is? Maple Lake? Yes. And they have a boat, and we went out there a few summers ago and water skiing and tubing and all kinds of fun stuff. And I remember at one point my nephew, who was at the time, he was probably 16 at the time, says, so about your age, says to his dad, he wants to go cliff diving. He found this cliff. They had found this cliff somewhere around this lake, Maple Lake, and he wants to go cliff diving. He wants to show us this cliff and jump off this cliff. So we go there, and we pull up the boat by the edge of this cliff which looks pretty high. Okay, this cliff which we climb up, and it wasn't all that hard to climb up. It was almost straight up, but there was ledges, so it wasn't like it wasn't like I had to rock climb up this cliff. I get up there, and I look down, and I thought, oh boy, when I was in the boat, this looked high. Okay, when I'm standing up here looking down, this looks really high. And I said to my nephew at 16, he had done it. He had already jumped off this cliff before another day. I said, I don't think I can do this. I don't think I can jump. He says, well, you don't really have a choice because there's no way down except to jump. So it was a cliff that you could climb up fairly easily, but you weren't getting down it without jumping off it. So thinking, how high is this thing? Drop a rock from this cliff, and kind of in your head, kind of time how long it takes to fall. What's the purpose of that? Well, if we know roughly how long it takes to fall, and we know that gravity is about negative 9.81 meters per second squared, then we can do a rough calculation of displacement. We can do a rough calculation of how high the cliff is, right? I think we found it was about 15 meters, which is 10 or 15 meters. It was 10 or 15, I think, which is high, but not nearly as high as it seemed when we were standing there at the top ready to jump over. It probably took me about 10 minutes to actually get the courage to actually jump off of this cliff. When I did, after the first time I jumped off it, then I was keep going back and back and back and jump off and jump off and jump off again. It's one of those things that it's terrifying the first time you do it, but then it's fun as soon as you actually step off the ledge. So you can do this, right, guys? This guy cliff diving in Mexico is actually going to figure out how high this cliff is, and it's a pretty accurate way of measuring how high the cliff is. Although I probably wouldn't do this. I probably wouldn't throw it downward with an initial velocity of 4, because that just complicates the problem, right? It's easier if we drop the rock. If we drop it, VI is not 4, VI would be 0, which makes the problem easier, right? Especially when you're trying to do it in your head, like we were that day. All right, so what do we got here? Is this a group A problem or a group B problem? It's group B, right? The object, the rock, falls at a rate of 9.81. It accelerates at a rate of 9.81 downward. It's group B. I'm going to write that acceleration down right now, actually. What else we got up here? We got the time of 2.50 seconds. Is that a negative time since it's falling downwards? Why is A negative, but T is positive? Cody? Good. Acceleration is a vector. Direction matters. It's going downward, so direction matters, right? Time is a scalar, so even though it's going downward, it doesn't matter It doesn't affect the time, right? Yep. Yep. What else we got here? We got something is 4.00 meters per second. Tell me what that is. It's VI, right? If you drop something, it's VI 0. If you throw it, it's not 0. And what are we looking for? How high is the cliff? Really, we're looking for the displacement of the rock, right? How far does the rock fall? That's going to basically give me the height of the cliff. Yeah? No, that's a good question, though. That's a good question. Question that Anthony asked, guys, if you didn't hear that, was, couldn't you say that VF is equal to 0? No, because when you're analyzing the trip down, the initial velocity is how fast is it moving the instant it's influenced just by gravity. So in other words, the instant it's leaving your hand. So we're in agreement that that's 4 meters per second, right? VF is not the velocity that it's moving after it's hit the ground or hit the water. VF is the velocity that it's moving when it hits. So how fast is it moving when it hits? Not 0, right? Here's another question. Couldn't we get VF if we multiplied acceleration by time? Yes. Yes, we could. Not quite, actually. We could get delta V by multiplying acceleration times time, right? That's A is equal to delta V over delta T rearranged. So we'd get the change, not the final. But close, right? Close. Here's the thing, though. That's not what we're looking for, right? Does that mean it's wrong? No, of course not. You get VF or delta V there. That's absolutely correct. But it's not what we're looking for. Maybe we can use that to help us out with another equation. Or maybe we could just find an equation that will work with the variables that we have given to us. Okay? Let's try D is equal to VIT plus 1/2 AT squared. How about that one? VITA looks good, right? I was hoping somebody would stop me. Nobody has. So I'm going to have to bring it to your attention now myself. There's a mistake with what we have up on the board, right? It's a small one, but it's an important one. Anybody see what the mistake is? Boy, that was quick. You guys got that. The initial velocity is negative 4 meters per second squared because, Mackenzie, you're right, because it falls downward initially at a rate of 4 meters per second. That might not seem like a big deal, but it is. Okay, you try putting positive 4 in here and then calculate it using negative 4, and it's a completely different answer. So we get negative 4 times a time of 2.50 seconds plus 1/2 of negative 9.81 times a time of, once again, 2.50 seconds. This is negative 10. Subtract, because it's negative 9.81, right? Subtract 0.5 times 9.81 times 2.5 squared. Subtract 30.65625. So if you had made this positive 4, imagine this would be 10 minus 30, as opposed to minus 10 minus 30. This gives us negative 40.7 meters. The other way would have given us negative 20.7 meters. That's a big difference, right? Is that our answer? How high is the cliff? Well, not really. This is the displacement of the rock, how far the rock falls, right? What's the height of the cliff, though? Well, technically, it would just be 40.7 meters. Listen, though, if you leave it like this, I'll mark that right. Even though technically it's displacement, not the height, that's fine. Don't worry about that, okay? Make sense? Yeah. This question any harder than anything we've done thus far? No, it's, in fact, you could argue that it's easier because we're given the acceleration in this question, and we're given the acceleration in all of these questions. Okay? Let's try these 2 questions, these 3 questions, actually. Tell you what, these 2 questions, just questions 1 and 2 here for now, okay? All right, let's have a look at question number 1. We'll at the very least set it up and show you how you would go about doing it here. says if a rock takes 0.750 seconds to hit the ground after being thrown downward, that's a big word actually, thrown versus dropped. Why? What makes this question different when it says the rock was thrown down versus dropped? Good. If it's dropped, VI is 0. If it's thrown, VI is not 0. Now, what is it thrown at? I don't know. That's what we're trying to find, in fact, right? But it's important to know that there is a VI, whatever it is. It's dropped from a height of 4.8 meters. Determine the rock's initial velocity. Let's say, for question number 1, the time is 0.750 seconds, and something is 4.80 meters. What is that? It's displacement, isn't it? And A is negative 9.81 meters per second squared. If it's under the influence of just gravity, then A is negative 9.81. If there's some other forces, well then A isn't 9.81. Okay, but that looks like it's all we have here. If we neglect air resistance. Anything else here? Looking for VI. Oops. Anthony, is VF equal to 0 here? When it hits the ground, is it moving at 0 meters per second? No. After it hits the ground, it is. Okay, but not when it hits the ground. So good. We don't know what VF is. There's a mistake up here. Anybody catch it? Yeah, Cody? Yeah. It falls 4.8, right? The distance traveled is 4.8, but the displacement is negative. Because really, when we put, I didn't say up at the top here that up is positive and down is negative. But if we made this negative 9.81, then down is negative. Therefore, the displacement must be negative as well. What do you want to do here? I'm thinking D is equal to VIT plus 1/2 AT squared. Now this is a bit tricky here because we got to solve for VI. Bear with me on this one, okay? And please follow along closely. Remember what we got to get rid of first here. Get rid of what is not attached. What's not attached to VI here? What's not attached to VI, Cody? The other side of the equation? Okay, half AT, that should be AT squared, shouldn't it? 1/2 AT squared. Solving for VI, get rid of 1/2 AT squared first. How do we get rid of that, Cody? No, we divide it if it's multiplied by VI, but it isn't multiplied by VI, right? The T is multiplied, but we're not getting rid of it yet because it's attached. Okay, 1/2 AT squared is not attached. How? It's added, right? So how are we going to get rid of it? Good. We're going to subtract D minus 1/2 AT squared equals VI T. Now we got to get rid of what is attached, which is the T. And Cody, how do we get rid of the T? Right, it's multiplied by VI, so we get rid of it by dividing. D minus 1/2 of AT squared divided by T equals VI. That's kind of an ugly looking equation. It's not neat and it's not tidy at all, but it's correct. Okay, plug in the numbers there, and let's see if you can get 2.73. Should work out to be negative 2.72 meters per second, right? All right, let's take a look at question number 2. Let's have a look at number 2 now. Having scored a touchdown, a football player spikes the ball in the end zone. If the ball was thrown down, again, that's an important term there. It's thrown down. That means VI is not 0. Thrown down with an initial velocity of 2 meters per second. You know what? I'm going to make a little note there because we've seen this enough times now. If it's thrown downward, it's negative. The initial velocity would be negative. From a height of 1.75 meters, that's going to be negative as well, right? Because it's moving downward 1.75. Determine how long it's in the air for. It's a group B problem. It's an acceleration problem. VI is negative 2. My displacement, how far the ball goes down, is negative 1.75. Should just be meters. Should just be meters there. And what else we got here? A is negative 9.81 meters per second squared. Looking for T. This isn't looking pretty here. How many people got this? Anyone? It's a hard question, actually. Why? Because I'll tell you what, the equation that I think of when I see this, my group B equation, D is equal to VIT plus 1/2 AT squared. How many people thought of that one? First thing that I thought of. Okay, look at my givens. VI, perfect. T, don't have it, but I'm looking for it, so that's okay. A, got it. T, looking for it. D, got it. Perfect, right? The problem is, I want to solve for T, and it's in two places. Now, if VI was 0, that'd be fine, but it's not. So how do I solve for VI there? You got to use a mathematical thing called the quadratic equation. Most of you will have never seen the quadratic equation at this point. Maybe all of you. None of you will have seen the quadratic equation. Good news is, there's another option. So this isn't going to work for us because we can't solve this. Okay, it looks like it should work for us, one unknown, but we can't solve it. We don't have enough math background to solve that. You will by the end of grade 11, by the way, but not right now. So how do we do it? Let's find something. It doesn't have to be T. Let's find something. Let's go VF squared is equal to VI squared plus 2AD. Okay, we got VI, we got A, we got D. All right, let's find VF. It's not what I'm looking for, but it's something. Why did I drop the negative there? VI is -2, isn't it? I just made it 2. Why did I drop that negative? Well, when I square a negative, it becomes a positive, but that's not why I dropped it. What is VI is equal to -2 meters per second? What does that stand for? What is this? What is that number? The initial velocity, yeah? What's this one, VI? The initial, no, speed. No vector sign over, right? I don't want a direction with this, right? So I drop the sign. It's just 2 meters per second and then square that. 2 times A is -9.81. D is -1.75. Pull out the calculator and see what we can get here. Let's say 2 squared plus, use some brackets here, 2 times -9.81 times -1.75. And now let's square root that. And when we get that, it's 6.1915. What did I say, 1915? Meters per second. Final answer? No. But it's something else we have given to us now. Now, I want to find T. Maybe we could just do something like this. Rearrange that to solve for T. The T goes up, the A comes down. Delta V is, what is delta V? -6.1915 minus -2. Why the -6.1, by the way? We got positive when we just solved for it. What do we solve for there, Mackenzie? No, we didn't. What's that 6.19 right here? It's not final velocity. Final speed. What do we need when we plug it into this equation? We need final velocity. Now, the final speed was 6.19, but we're smart enough to recognize that it's moving downward, right? So we can just tack on the negative there and make it -6.19. This is kind of odd. Subtract -2, final minus initial. Hey, if the initial is negative, it's going to be subtract a negative. We do that math. I think it should work out to be 0.43 seconds, I think. If you had have used D is equal to VIT plus 1/2 AT squared and use the quadratic equation that you will learn in Math 20, you would get this answer. It's just that you don't know how to do it yet. I promise you in Physics 20, I'll never give you a question where you have to use the quadratic equation. If you learn it in a month and you're good at it, great, go ahead, give it a whirl. If you don't like it, there's always another option like this. Let's try one more example and then we'll wrap it up for the day, okay? Page 59, a clown throws a ball upward at 10 meters per second. Find the maximum height and the time that it takes to do so. Yep. What do we got here? It's a group B problem, right? We know it's a group B problem. We know that VI is 10 meters per second, and it's 10 meters upwards. We know that A is negative 9.81 meters per second squared. Negative because it slows down as it goes up. Doesn't matter whether it's going up or down. Slows down going up, speeds up coming down. Doesn't matter. We're looking for the maximum height. Well, that's the displacement, right? And the time. Is there anything else we have if we read between the lines? Yeah. What is it? Oh, VF is 0. Is he right? If it goes, remember the keys I threw up into the air? Showed you that example of the keys going up into the air. They slow down, they slow down, they slow down. When they reach the max height, they stop, only for an instant. But if we're only analyzing the trip up, VF is 0, right? So we're going to say VI, A, VF, looking for T. I think we can solve for T first. I think that might be the way to go, right? Doesn't matter what order we solve this in. T goes up, A comes down. Delta V is 0 minus 10 over negative 9.81. What is that going to be, like 1.1? 1.0194 seconds. We're going to round that to how many digits? 4 digits? 3 digits. Because that's 3 digits. 1.02 seconds. All right, let's get the max height now. D. Let's say, let's try VF squared. VI squared plus 2AD. Solve for D. Get rid of what is not attached first. Stephen, what's not attached here? What's not attached to the delta D? Good. The VI. Yeah, the VI is not attached. So how are we going to get rid of that? Good. So it becomes VF squared minus VI squared equals 2AD. Now we got to get rid of what is attached, right? Cassie, what's next? What are we going to get rid of next there if we're looking for D? So, yeah, divide by what? No, we're looking to solve for D. So we're going to divide by what's left here? 2 in the A, right? So we're going to take 2A over to the other side by dividing. Becomes VF squared minus VI squared over 2A equals D. VF is 0 minus 10 squared over 2 times negative 9.81. Let's see what we get here. 5.09, 5.1. Yeah? Let's have a look for the last few minutes of class and for homework, if you don't finish it, at this one question on page 59, please.